All right, guys, so what we're looking at is the electric field, a distance of d above the center of a rod of charge. So what I would want to do is go ahead and break that rod down into a whole bunch of little tiny dq's, and then I'd like to look at the geometry of this bar. If I'm looking at symmetric charges about that center axis, I can see that those two electric field vectors are going to cancel in the x direction, right? This one's going to the right, this one's going to the left. So it tells me that E in the x direction is going to be 0. It tells me that we'll only be considering the electric field in the y direction, okay? The other thing I want to look at is if I look at a couple of different geometries as I change dq, as I go to different dq's, what's going to happen very simply is you notice that r and theta are changing. So both of those are going to need to be considered variable here, both r and theta. But for our geometry, it's pretty simple. We do have a nice right triangle here with r being the hypotenuse. So the distance from our little tiny dq to our point P is our hypotenuse. The height of all of these right triangles is going to be capital D, and the base of those triangles are just going to be the position of each of those dq's that we want to consider. So again, when I look at this electric field and the contribution to the electric field dE, it's in this direction. Okay, and I know I can break that vector into its components, so x and y. And the one thing I want you to notice here, if I'm looking at the right triangle here with my dq, and then the right triangle here with dE as the hypotenuse, that theta has to be the same. Those are similar triangles right there. So then DEY is just going to be DE times the sine of theta. Okay, so I'm going to go ahead and bring this guy into a smart notebook. So we have that image there, and we'll bring it to a smart notebook where we can go ahead and do our integral. So let me paste that guy in. Okay, so we've now got we've now got to consider each of the little tiny dq's along this bar of length L and total charge capital Q. So I'm going to go ahead and just slice off a little chunk of this bar that contains my dq. This bar is one-dimensional, so it means we're going to be using a lambda for a charge density, or a linear charge density, charge over overall length. And any little tiny length that I cut out of this bar, the ratio of charge to length should be the same. So what I want to do, I've called it dx. Let me explain really quickly why I'm calling it dx. First thing we want to do in each of these problems is put the origin of your coordinate system at the point P. So if this is my coordinate system, there's my x, there's my y. Well, the y distance for every one of these charges is going to be capital D, right? So that's not changing for any of the dq's. The y distance is capital D. But for each of my dq's, the x is different. So I want to call this x, right? In this coordinate system, the position of that charge is negative x, right? Okay, so that's my x position, hypotenuse is r, and the height is d. So now I want to take that little tiny dq with a length of dx, and I want to go ahead and integrate over all dq's. So what I'm going to say then is the electric field in the y direction is equal to the sum of all the little contributions to the electric field in the y direction from 0 to the total electric field. And that will be equal to the contribution from each of the tiny charges. That's, again, k dq over r squared. That's dE for each of the little tiny charges, but I only want the y component, so I'm going to say times the sine of theta, right? And when I write this integral, I see right away that I've got lots of problems. I've got a small factor of q, but I've got both r and theta are variables. So I need to do a lot of changing up here and a lot of geometry to look at. So I'm going to look at this right triangle right here with little r, and I notice that if I write r in terms of Pythagorean theorem, r squared would be d squared plus the position x squared, right? So I can go ahead and substitute for that down here where it says r squared. The other one I want to take care of is sine of theta. Well, same triangle. If I look at the sine of theta is opposite over hypotenuse. So this is going to be d over r, but now I've just got another lowercase r. I had just tried to get rid of it with the r squared up here with Pythagorean theorem, so I need to do one more step to get rid of this little r in the denominator. And what I'm going to say is, well, if r squared is d squared plus x squared, then r is just the square root of d squared plus x squared. Okay? And now I'm prepared to substitute both of those into this integral. So EY is just going to be the integral of k dq over r squared. Well, we said r squared was d squared plus x squared times the sine of theta. Well, we said sine of theta was d over r. So that's d over r, which is d squared plus x squared to the 1/2. And the next thing I'm going to do, just to make my algebra simple, is I'm going to say this d squared plus x squared to the first is the same thing as d squared plus x squared to the 2/2 power. And now I notice I have those same terms on the bottom. If I want to multiply them together, it's going to be adding the exponents. So this becomes integral of, I'm going to try to write this a little bit nicer with the small factor at the end. So that's kd over d squared plus x squared, 2/2 plus 1/2 is to the 3/2 power, and then dq. Great. But I'm still in a bind because x and q are not the same variable. So I do need to make a change to that dq. And the way I'm going to get that change is by looking at the linear charge density, right? This little length of bar should have the same ratio of charge to length as the overall length of the bar. So I'm going to write that again, that lambda is dq dx. So then dq can be written as lambda dx. So my electric field in the y direction is equal to the integral of k times d all over d squared plus x squared to the 3/2 times dq, which is just lambda dx. Okay, this is actually a pretty ugly integral, to be perfectly honest. The last thing I would do is, I kind of made up lambda, that linear charge density. I would need to substitute q over L back in, but this is as far as College Board would expect you to go. This type of integral is not simple. It takes a substitution and some higher level calculus to do this integral. So we're going to stop here. In terms of a free response question, this might be part A and B, get me to here. And then what College Board is going to say is, okay, then part C, the solution is this, and then have you move on. If you were to do this at home, a lot of times you could either try the substitution or you would go to an integral table, find an integral in the integral table that looks similar to this, and then that solution would already be in the table for you. We don't have this in our integral table on our equation sheet, so this is not an expected integral for you to do. You will be expected to take it to here, though. This is a possibility for the AP exam. Okay, so the next thing we're going to do is remove some of the symmetry. In the next video, we'll move this point P over so that it's not above the center of the bar, and we'll see how that changes our integral slightly. Okay, I am noticing now that I didn't make this a definite integral. I would like to add integration bounds. So really quickly, if I'm integrating in the x direction, if this is my coordinate system where the origin is here, I want to integrate from the beginning of the bar to the end of the bar. So to the left side of my origin, I would be going out as far as minus L over 2. And to the right side of the origin, I'd be going out as far as L over 2. So let me go ahead and put those integration bounds in, minus L over 2 to L over 2, and that's as much as you would need to do for AP. Okay.